Hey everyone, so I finally got the test fixture all done and I want to take you on a tour through it. This has been kind of a cool side project that was kind of required in order to be able to reliably test the Spirit board, and it took a little bit longer than I expected, but I put the time into it and really did it right, and I'm really happy with the way it came out. It's going to test everything, so we can test a board as if it's in the real robot without having to actually put it together, and it'll tell us if everything passes, and if there's any fails it'll tell us exactly what went wrong. So I want to take you on a quick tour through it and show you how it works and what it does. Okay, so I'm thinking about a test fixture where we're going to take the board that we're going to test and we're going to connect ribbon cables to the bottom headers. I'm going to get a ribbon cable that matches this pin out so I can just plug in all the connections at once, and that ribbon will come along to another board on the side where we will take a couple of motors and we'll stick those on there, and we'll put little flags on the shaft so that when we spin either direction we can watch that. We'll mount a couple of servos up and we'll have little flags on those so that when we send test signals to them, we'll make sure that it controls all the signals, or that it controls all the servos like it's supposed to. And then I'll put an ultrasonic rangefinder on there, and I'll have a barrier set up for it that's a known distance away. And so that way we can run a test program on here that'll test all that stuff all at once. Whoever's doing the test can watch, make sure everything moves like it's supposed to, and then the idea is we're going to send the signals out of the USB back to a companion laptop, and we're going to use processing, it looks like we went with, and that's going to create like a user interface where it'll show the test results. And so we'll be able to see all the internal tests that it does, we'll be able to visually see that it runs the hardware on the outside like it's supposed to. So in an effort to make the whole thing run fast, I'm thinking to put a little more time into the test fixture so we don't have a bunch of janky wires all hanging all over the place, and we don't have a rat nest of stuff everywhere. We've kind of tested stuff like that in the past, and it becomes just a mess to deal with the test. And then you've got making and breaking connection, and you know, it's a hassle to test at that point. So I'm going to really put the time into doing this thing upright, and hopefully this test fixture will be a little bit of a work of art in and of itself. And then we'll just be able to push these boards through as quick as we can. We'll do a good thorough test on everything, and then we'll have high confidence that every board's good when we send it out. So here it is all put together. We CNC'd a bunch of pockets in this out of a block of ABS plastic, I believe this is. This is just some scrap stock we've had sitting around for forever, and it worked out perfect for what we needed. There is a whole space that's cut down into here that allows all the cables to drop through the bottom. We'll plug in a ribbon cable which goes over to a Raspberry Pi, which is going to be configured the same as the one that's inside the robot when it's all assembled. And we've got this ribbon cable here that reaches across to this little breakout board that I made through another bit of scrap stock that I had, and that breaks out the control lines to the motors, the ultrasonic rangefinder, and the 3 servos. So that way we don't have to go and individually plug them into every single board as we test them. We just have one ribbon cable, we stick it on the bottom, and then it hooks everything up. Then we have the wings broken out, we have the eyes broken out, and we have the 3 bottom sensors, the edge and bottom sensors. That's one right here, and one right here. And then we test the ambient light sensors, which are here, here, and here, and we'll measure the ambient light that's already in the room. And then we also have some IR light sources here. We've got 1, 2, and 3 that fire straight into the sensors, and that works together with this board over here, which is an Arduino that goes to yet another breakout board that we have, and that flips the light sources on and off at certain timings. So we can test and make sure that, you know, the level of what the ambients are seeing drops down to what we expect in the room, and then we can blast it with light and it'll bring it up to almost the max, but not all the way to the max, because there's some little pull down resistors that are in that circuit, and if there was something wrong with one of those pull down resistors, if it was missing or pillow connection or something like that, then that measurement would go all the way to the maximum at the top. So by seeing it at a certain level, we know that it's, you know, the resistors are working like they're supposed to. So the way it works is once you get everything plugged in, you power it on, and we hear 3 beeps there. That tells me that the piezo is working correctly. And then it starts off where it drives all of the pixels to red, green, and blue, and then white. And then it also powers up the Pi. And once the Pi boots up, which takes a few seconds, it'll turn the 1 pixel green, and then it will start doing this animation sequence on the wings. And that tells me that the circuit controlling the pixels from the Pi works, because there's actually 2 circuits. There's one that comes from the Arduino processor and one that comes from the Pi. and they're at different voltages. So they go through a little part right here that basically matches the voltage when it goes into the first pixel. So by controlling them from both ends, that tells me that the whole system's working correctly. And also because the pixels, they work like a daisy chain. So you send data to the first one, and then it sends it to the next and the next and the next. So if you break the connection between them, then you don't get data that passes through. So that's why we have them all hooked up here. So that tells me that, of course, we're not testing the individual wings here, but the wings work. And then that tells me that the data is getting back over and it's getting through the board to the next connector. So if I had a wing that wasn't animating for some reason, that would tell me that maybe there's a pin off on one of the connectors or something like that. So when we first power it up, we do a manual check before we do all the automated stuff, and we test the accelerometer and the gyroscope first. We have a readout on our test software that's going to be connected to it, where the serial port, you can see the serial port's reporting right there. It's sending data back to the computer, and it's the readings coming out of the accelerometer and the gyroscope. So we're going to do a physical manual movement of just nudging the board like this, and then rotating it, and the numbers should update in millimeters of how much we've moved it. So if we nudge it forward, we should see 5 or 10 millimeters, and then we should see negatives, and then we should see negative this way, positive this way, and then when we rotate it, we should see a positive of 5 or 10 degrees and a negative 5 or 10 degrees, and then we'll just sit and watch and make sure that the numbers are stable and they're not bouncing around crazy. And so that tells me that we're getting good clean readings. It can talk to both of the parts, and so that basically passes the accelerometer and the gyro. Make sure that they're all soldered down, all the pins are good and all that. Once that test is done, we hit the button, and that clears it out of the manual test. And the next thing we're going to do is it's going to automatically run the motors slow in both directions and then fast in both directions, and then it's going to sweep the servos. And then it sweeps the servos. And when I put these horns on here, I intentionally put them on here a little bit off. There's a calibration that you can adjust in the software once you build up your own Rover, where you can set the exact center position of the servo, because anyone that's ever tried to mount anything to a servo before, you know that you can never get it exactly straight. It's always off a tooth or whatever. So you can put a number in there and it'll recenter it. So the fact that they're all nice and straight, that tells me that that part of it's working. And by running the motors, by running them slow, we send a PWM signal to them, which to the driver anyway, which drives the motors. And if that wasn't oscillating on and off correctly, then you would get just fast both times. So the fact that we can drive them slow and then drive them fast, and that we can drive them in both directions, that proves that the direction control is working. It proves that the high speed is working, and that we're delivering about the amount of power to it that we expect, because we'll see how fast they turn. And then the fact that they move nice and slow in a controlled way, that tells me that we can dial down the speed. So that proves that all the signal lines are going to the motor driver correctly, and that the motor driver is functioning the way we expect it to. So once the manual checks are done, the whole rest of the test is automated, and we can determine if everything is good to go within a few seconds just by looking at the display that comes out of the software that I wrote. To make sure the serial data can talk to these ports around here, we've got this little loop back going right here, so that as the serial data comes out of the PIC, it goes right back into it over here, and we make sure that the Arduino can then reach out and send that data out and then retrieve the response back. That's another test that we do. There's several different power rails that are on here. There's the battery direct line, there's a 3.3 line, there's a 3-volt line, and there's a 5-volt line that control all different kinds of stuff. And we can directly measure the 3-volt line by just determining that the responses or the measurements on the PIC are correct. If that was at a different voltage, then the readings on the PIC would be different. So we kind of test that in kind of a roundabout way. But to make sure that the 3.3 volt bucking power supply and the boost supply that's running for the 5 volt is operating correctly and that they're at their correct voltages, we are measuring with this rail right here. And so we just take this connector and we drop it in there, and that runs around to the Arduino, and we're doing an analog to digital conversion on the Arduino, and so that tells me what that voltage is, and then using this serial port over here, it reports that back to the computer also, and then it pulls those numbers together into our main test. So in that way we can determine that all the power rails are working correctly. We do occasionally have, it's pretty rare, but we have the same 3.3 volt supply on our Ringo robots, and there's a resistor on here that sets what voltage it's supposed to go to. And so if that resistor was not populated, or it somehow got the wrong value on there, then this would regulate to the wrong voltage. And everything might appear to operate the way it's supposed to, but it might still be the wrong voltage. So that's why we do a test like that, to make sure that it is the correct voltage. And the same thing with the 5-volt supply. We want to make sure that we're putting out, you know, right at 5 volts or within a tolerance of 5 volts, and that it's not regulating to, you know, 4.2 or 7 or something like that. And so that's why we test that, and that determines that all the power is working like it's supposed to. And then once the manual tests are done, the whole rest of it is pretty much automatic, and that's what you're seeing right here. So this stuff all looks pretty overwhelming, but don't be overwhelmed by it. This is more for our purpose, to make sure that everything on the board is functioning the way it's designed. So when I'm talking about all these buses and everything, that's nothing that you need to really worry that much about as an end user, like the SPI bus and the I2C bus, but that's really important for us, because that's what actually transfers the data at the low level. For your point of view, you're going to use some functions that are going to go and make all these things work all by themselves. So as far as you're concerned, it's going to be simple little functions, like if you want to read the voltage or something like that, it'll just give you a result. You don't have to worry about selecting a bus or anything like that. The whole system all works by itself. And with this display, you can pretty much see everything that's happening on the robot all at once. I built this whole thing in Processing, which is a free software. It's very similar to Arduino, and you can build stuff like this. You can talk to Arduino boards or other electronics with it. You can build little apps that just work by themselves. You don't necessarily need to talk to anything outside. And this was suggested by some of the backers on the Kickstarter, so I want to thank you guys so much. You guys saved me so much time doing this. It looks pretty complicated, and it was, but getting started and figuring this out and doing this, it was not that hard. It was time consuming, but it's not like I had to learn some brand new, you know, software package that I didn't know. For the most part, I was able to follow examples and figure out how to do this. And basically all it does is it just runs through a big loop, and it just reprints the screen constantly. And there's a bunch of global variables in the background that are represented by all these. And then I have a serial packet that comes in that's like 80 characters long, or 80 bytes long, and it's got all this data in it. And so it unpacks the bytes, and then it loads it into the variables, and then it goes through every single one of these tests, and there's a pass-fail on every one of the tests, and so it'll determine whether it's good or not. So we've got the surface sensors. This is the 2 left sensors, the 2 right sensors, the 2 rear sensors, and I have a pass-fail that's in there of what they should be reading. I can see these are my charges. I can see that the charge indicator line is telling me that the charger is present, because I've got a USB plugged into it, and it can charge off the USB, so I should see that. And I'm seeing that a charge is in progress, and I can see there's a little, the charge LED is lit up on the robot also, but that tells me that this line that you can pull from your software is functional like it's supposed to. The rangefinder is online. That means it's actually getting data back from the rangefinder. It's measuring the range. There's a little wall that's built onto our test fixture that's about 70 millimeters away. And occasionally I'm seeing this number drop down below 70, and I'm not exactly sure why it's doing that. If I look at it on our scope, everything looks fine, so I'm not sure, but it's occasionally it drops to 63 or 65, but for the most part it's pretty well locked in there at 75. But if the circuitry that converts the voltage level from the rangefinder back to the processor was not working, or again if there was a resistor missing, or the part was on there backwards or whatever, then this would not be getting a response at all. So we would see that that's bad. The range counts tells me how many pings it has gotten back cleanly without it being wildly out of whack, and it just stops that at 250. Once it gets to 250, I don't let it keep going beyond that. The UART loop, that tells me that the software is able to send data from the Arduino processor to the PIC processor. The PIC processor sends it out the serial port through the serial mode selector switch, which selects which of the 4 possible modules is selected, whether that's like the Wi-Fi module or the XP module or whatever. It goes through that part, which proves that that part works, and then it goes back in the other direction, and it goes back into the PIC processor, and then the Arduino comes along and unpacks that, and it matches and it makes sure that the packet that it sent matches the packet that it received, and if it does, then it gives it a pass. And so if I disconnect that little loopback wire on there, you'll see that it goes from pass to fail pretty quick. So yep, it's failing right now because it's not getting data back, and once I reconnect it, then I go right back to pass. I've got my ambient sensors when they're turned on, turned off, and these are all within the pass range here. This is the voltage that's actually being measured by the processor on the board, so it's telling me my battery has 4.1 volts in it, which is about what I expect. I'm mainly looking to make sure that that's not some really low or weird number or whatever that would tell me that that part of the circuit's not working. This is a live measurement of current. The board's drawing about 375, 400 milliamps, which is what we expect. almost all of that goes into the Raspberry Pi, and the majority of that current actually goes to the USB controller on the Pi board, from what I understand. It does draw a pretty incredible amount of power for the most part, just kind of sitting there idle, but that's the way it works though. This is what's being measured by the off-board Arduino processor with that jumper wire that I showed you that's measuring the power rail. And so our 5-volt power rail is sitting at 4.98, which is pretty darn close. Our 4.2 volts is sitting at 4.17, which is actually more that's actually battery voltage. We call it 4.2, but that's actually just the voltage of the battery. And I'm matching that against this number over here, and they should be pretty similar because I'm measuring basically the same voltage from two different places. The 3.3 line should be regulating. It's right there at 3.3. It keeps jumping up, but that's just because this connector, it just sits loose in the port, and if I wiggle it, it comes loose, and if I bend it over and hold it tight, then you get good clean readings on it. And the regulator on this particular board is regulating a little bit low. It's more like 3.2 volts, but that's still within the pass-fail range, and so that's perfectly normal. But we're mainly making sure that this isn't at 2.2 and making sure it's not at 5 or something like that. The I2C, which is the main bus that we use to talk to the PIC processor, that's telling me that I'm getting data there, and the fact that I'm able to read all this other data is also telling me that that works correctly. My 38 kilohertz is showing fail because I haven't shot any data at it yet, but I'll grab the remote and send some data into the sensor, and it goes straight to pass because it got that data. And let's see, this is the voltage that was measured by the Raspberry Pi when it measured the same thing. It did its own communication with the PIC processor to determine that what it thought the voltage was, and so that proves to me that the I2C is working correctly on the Raspberry Pi and that it's able to talk to our target board. And the current that it measured when it booted up, it freeze frames this. It doesn't keep reading it over and over and over, but it tells me that as it was booting up, it got a snapshot of that current. And you know, if that had come back something really weird or nothing at all or whatever, that would tell me maybe there's something wrong with that the I2C connection. The SPI connection, that's one of the other buses that we use to talk between the Raspberry Pi and the Arduino, and that's how we control motors and do a few other things. And it's just sending a packet over and over and over, and every time it gets it correctly, it increments this number all the way up to 250, then it stops, and every time it gets the wrong packet back, it'll increment this. So you can see it's always getting the correct packet. And the SPI works both directions, so you send data one way and at the same time the other device sends data back. And this is the Pi telling me that the data that was sent to it matched what it expected to see, so it proves that both directions on the line are working at the same time. There's also a couple of interrupt lines that you can program in your software for different functions, and this is making sure the main one is int1. That's kind of the general purpose to signal between the different processors, and we don't have it doing anything particular right now, but it's kind of like for your use if you ever want to use it for something. And to make sure that it's cleanly going up and down like it's supposed to, we run it low for 50 milliseconds and then high for 75 milliseconds. And so this is just reporting back how long it was high and how long it was low. And then the last couple of tests that we do is there's one of the other interrupt lines is just twiddling up and down by itself. It just goes high and low and high and low, and it just reads it on the fly right there. And so I'm just making sure that this is going 0, 1, 0, 1 and making sure that that's operating. And then these are both tied to the button right now. And so if I push the button, I just make sure that that goes low. So that goes to 0 when I push the button, which tells me the button's all connected, and that's working. And so when everything is all lined up in green, and we don't have any reds, we're kind of right on the edge right there with the 3.3. But you can see that once everything goes green, you'll get a pass down here. And so now that we can hold everything's green for a few seconds, I would say that that's a pass. Everything's working on the board now that I'm holding the connector in place. And then down here at the bottom of the screen, I have a readout from all of the important registers on the PIC processor. And so this tells me what the PIC is doing at any time. So it tells me by looking at all these ones and zeros, I can determine every single pin, if it's high or low, whether it's set for an input or an output, whether it's in analog mode, some of the status registers that you can pull to determine what's going on. I can see what those are. And so we don't really look at those in the test, but it was easy enough. As long as I'm getting all this data, I may as well unload all that at the same time. I figured that's probably useful that, you know, if we do have a failure going up here or something, then maybe we can look down here, and it's just probably just good diagnostic data. And as long as I'm doing it, it's really easy to do that. You can do this same sort of thing in the software that you write the software for the PIC in, but you have to plug it in, turn on a debugger, you have to set these breakpoints and then run it in debug mode, and it's kind of a big thing you have to go through. And so having something we can just plug into and just boom, get all the data out of it, that's convenient right there. So this is all the code that's loaded on the Arduino processor right now, and this is the whole test sequence. There's quite a bit to it, you can see. So like I said, we're doing a lot of low-level testing, but some of the testing that you're going to do is going to be simple things like this particular bit right here, serial print, surface left 1 will just automatically go out and read what the left number 1 surface sensor is reading, and that would give you a result back. So you don't have to worry about messing with the bus or anything, but when you call that, it actually causes the Arduino to go out with the I2C bus and go talk to the PIC, and the PIC will return whatever that reading was the last time around, and it runs in a circle every 20 milliseconds, so that's 50 times a second. It does that measurement, and so it's just going to respond back and say, hey, the last time I read my sensor, it was at this level, and it'll just shoot and so it says, you know, the last time I ran my circle, the sensor was, you know, whatever, and it just shoots the value right back, and then in this case it prints it to your screen. But you could also do something simple in your code, like saying surface sensor equals something like that, and it would just read it for you. So that's how the test fixture works. Hopefully that was educational to someone. Anyone else that's wanting to do something similar or build some sort of a fixture for a board or whatever, feel free to ask me questions. I'd be happy to share the software that I did in processing to show you at least how I got the data communication working back and forth. There's a ton of examples that are out there, so it's not real hard to find the information, but sometimes it's real helpful to look at an example that already works, and then you can just modify it from there. So we put a lot of time into it, but I think it's going to be well worth it, because we're going to be able to push these test boards through probably, I'm guessing, anywhere from 1.5 minutes to maybe 2.5 minutes for each test. So the big part of the test is going to be just bolting the thing down, or I guess rather plugging the wires into it. So now that we got the test fixture all up and running, we'll get to testing these boards. We've already run quite a few of them through the machine, and we've been testing a few kind of along the way just to make sure that everything was fine coming off the machine. And so far everything appears to be okay. And so hopefully we'll continue to have good luck with that. And once they come off of here, they'll be getting put in bags, and then they'll be sending out to you guys. So thanks again for watching, and thanks for your support. Bye.